Hello, in today's session I will be discussing explainable AI, also known as XAI. This is a relatively new field of study in artificial intelligence that has been getting a lot of attention lately due to its usage in making AI models regulated and accepted in the industry. I will be covering three main areas. First, what is XAI? Followed by descriptions of four methods, which include SHAP, which stands for Shapley Additive Explanations, LIME, which stands for Local Interpretable Model Agnostic Explanations. Then I would discuss what are counterfactuals, and then discuss LRP, which stands for Layer-Wise Relevance Propagation. I will then detail three major examples of applications in XAI. XAI started in 2015 with DARPA, which is the Defense Advanced Research Project Agency, essentially the Defense Department of the United States. DARPA was also the first ones who started the internet by creating a network that exchanged packets. Since 2015, XAI has become more and more sought out and more rigorously studied, especially for its use in our now global conundrum of how to accept AI in industry. XAI helps in making AI understandable, comprehensible, transparent, interpretable, intelligible, responsible, interactive, explainable, revisable, trustworthy, and accountable. These are all important ingredients necessary to make a legal case for the acceptance of AI in industry. For example, if we talk about mortgage approval, just having a deep learning model that accepts income and age as inputs and outputs a yes or no is not sufficient to make the AI acceptable. What is necessary is the understanding of how this approval is accomplished inside the box. This is where XAI comes in. With XAI, not only do we explain why the AI produced an answer, but we also trace back to determine what contributes to a problem, such as bias. This field of study is exciting nowadays, especially because of the legal issues associated with accepting AI in industry. SHAP, which stands for Shapley Additive Explanations, is a methodology whose essential idea is to give credit equally to all participants that contributed to a result. Let's say we have a model with the inputs of age, sex, blood pressure, and BMI, and we get an output of 0.4. Let us say that this output is probability to get breast cancer. This is wonderful. The model has done a prediction. However, what if we want to know how much of an impact each of these features has to that contributes to the output of 0.4? This is where SHAP comes in. With SHAP, we determine how each feature contributes to the prediction. The mathematical concept is SHAP values, a topic in game theory. Essentially, the intuition behind SHAP is that we determine how each feature contributes to the total score by removing each feature one by one and making calculations. However, it is not that simple. For example, one feature could work very well with another feature, i.e. they collaborate. Additionally, we must also consider subsets of the features and how they contribute as a group. Here's the equation for determining the Shapley value for a given feature I. Phi is the Shapley value for a given feature I. F is the AI model, and X is the inputs for a single row. In this summation, we iterate through all iterations of subsets of features X prime, which is just a subset of X. At the far right, we calculate how I's marginal contribution is by calculating all the contributions minus the contribution without I. The weighting emphasizes how much the given feature is worth. Here M is the total number of features. With LIME, Local Interpretable Model Agnostic Explanations, the goal is to simplify the model. The whole global outcomes could be a very complicated function. So instead of focusing on the whole global outcomes, we zoom in to the point whereby the classification becomes a linear issue rather than a complex function. Using a local model, we can more easily explain, with linear paradigm, why our data point belongs to a certain class of output. The title of the paper is very aptly. It's called Why Should I Trust You? Explaining the Predictions of an E-Classifier. At the left, we wish to get a local approximation given the inputs. Here the inputs are age, gender, and heart disease. The first term is a loss function that attempts to get the complex and simple models as close to each other given the input's neighbors. The last term is to minimize the complexity. Big G is the family of interpretable models such as decision tree, linear regression, etc. Essentially, the goal is to find the simplest model which matches the complex model within a given neighborhood. The essential key concepts are: number one, local interpretability. LIME aims to provide explanations for a specific instance rather than the entire model. It generates locally faithful approximations that help understand the model's decision-making process for a given prediction. Number 2, perturbation in samplings. Line perturbs the input features of a specific instance to create a dataset of perturbed instances. It then samples predictions from the complex model based on these instances. Finally, 3, local interpreter model. A local interpreter model, often a simple linear model, is trained on the perturbed instances and their corresponding complex model predictions. This interpreter model serves as a proxy for the complex model locally. Next, we have counterfactual. A counterfactual is a variable whose change makes an output change. If we look at the diagram with S being the original, the first one, in S1 we change the watch to a t-shirt, but the output remains a jacket. In S3 we change the basketball to a guitar, but the output remains a jacket. It is only in S2 where we change the tie to a tablet that the output changes from a jacket to a mouse. Thus, changing a tie to a tablet is a counterfactual. You may ask, why is this important? Let's say we have a patient that has irritable bowel syndrome. Here, counterfactuals are used to determine which foods cause abdominal pain. It is essentially a progression of elimination. Finally, we have LRP, which stands for layer-wise relevance propagation, and this is mostly done with images. The goal is to determine which areas of the image are the most important in making an output. Thus, we calculate the relevance layer by layer. In the example, the neural network takes as an input and outputs the class. Here we have a cat, and the output is the category cat. So how did this neural network make this decision? If we use LRP, we can trace backwards to the neural network. At the input, we see that there are darker colors for the cat's face, thus indicating that these areas are what the neural network's attention is focused. Here, the background image is almost not noticed, and it's just the face of the cat that's noticed. Mathematically, our calculations start from the end of the model and progressively goes to the beginning of the model. This is a form of backpropagation, but instead of classification, it is for LRP. Any given layer L and the node I, we do a calculation based on the value of the previous attached node combined with the multiplication of the attached weights in their corresponding nodes. This series of calculations are done progressively, layer by layer, from the beginning to the end. Thus, we can determine how much each input has an impact on the output. The first application is in electricity consumption for anomaly detection. We have a system that collects appliance consumption information such as a refrigerator, toaster, microwave, and television. However, suddenly at 3 a.m. we see an abnormal excessive usage of energy. If we use XAI, we can trace back to determine how much each application contributed to this abnormality. Here we conclude that it is the refrigerator that is malfunctioning. The second is in identifying a bias in the mortgage approval process. We have the inputs of income, age, profession, and postal code, for example. Then we learned that many Hispanic customers who would normally be accepted are being rejected. We trace back and determine that postal code is having the biggest influence in this rejection. We now can analyze and determine that these customers are rejected because they live in a Hispanic neighborhood. Finally, we'll discuss about using chest x-rays to diagnose disease such as COVID-19. As input, we have black and white x-rays. However, there's an overwhelming number of healthy patients that are being diagnosed with COVID-19. So we trace back to see where parts of the x-rays are contributing to this diagnosis. It turns out that there's a background noise, white specks, that are being wrongly classified as disease. Okay, we are at the conclusion of the presentation and we have 3 simple questions. Let's test your attention. First, we will start with a simple one. What does XAI stand for? That's correct, explainable AI. How about, can you name one application of XAI? In this presentation, we had 3. You just need to name one. Okay, we had electricity consumption anomaly detection, mortgage approval, checks x-rays to diagnose disease. And as a bonus, can you think of any other? Finally, I gave 4 XAI methods. Can you name any 2? The 4 are SHAP, Shapley Additive Explanations, LIME, local interpretable model agnostic explanations, counterfactuals, LRP, layer-wise relevance propagation, and there are many more online. Thank you so much for your attention. Goodbye.